Hi all, it's Dr. Clark again and another lecture for natural resources. And today we're going to progress into kind of the building blocks of environmental science. So we talked a little bit about how science is done, okay? A few examples of, where the world is at today when it comes to environmental science and resource management. But before we dive into um, element cycles and ecology and the basis for either renewable resources or non-renewable resources. And before we dive into that, we kind of need to talk a little bit about chemistry and the role that chemistry plays in all these systems. Now, I know that majority of you watching this might think chemistry is a very boring subject and a very difficult subject because that's the nature of um, you know the rumors that go around chemistry. Or maybe it's not a rumor, maybe that's your experience in high school or another class in college. But chemistry itself can be very, very interesting and integral in learning information about natural resources and why some natural resources are better than others, right? And how they come about, and then what are their uses. Okay, so let's dive into a little bit of chemistry of life. So natural resources are things that are not created by man, okay? Or at least a piece of the natural resource is not created by man. So therefore, we would consider that be chemistry of life. So it's things that have been created by living organisms naturally. Okay? Hence the word natural resource. Okay? So let's dive into this a little bit. So why chemistry? Why are we interested in chemistry? Okay? Again, like I said before, in order to understand ecology and biology and natural resources, environmental science, you really need to look at the base level first. Okay? And since ecology is the study of the relationship between organisms and their environment, okay, a lot of ecology questions come about: how does energy move throughout that environment? Okay? Or how does different elements move? Maybe we're looking at the carbon cycle. Maybe we're looking at phosphorus cycle and the nitrogen cycle. Okay, where is a lot of that material trapped in the environment? Okay? How does it get out of organisms and into another organism? Or is it stored in the water? Is it stored in the atmosphere? Is it stored in soil? Okay, where are these elements? Okay, where is this energy? Okay, and that's really the basis of chemistry. Okay, how chemicals can move and change and bond to each other, share electrons. This kind of stuff is really the basis of chemistry. So the elements of life, when we start looking at what building blocks, okay, do we need to have life, okay, we first need to talk about kind of matter in general. Okay, so matter is considered everything that has mass and takes up space, and it would include solids and liquids and gases and plasmas. Okay, and so there's four real states of matter. Now, this may change in your lifetime. I'm not entirely sure. There are individuals at Harvard, MIT, Berkeley, um, um, a few other places. I think University of Michigan. There's a few other places that the physicists in some departments have claimed that they've trapped light in crystals and therefore made solid light. Now you might ask, why would anyone want to do this? Okay? And I'll let you Google, there's videos on this and there's information out there, but just one possible explanation of why this might be of value is binary coding. So when we look at computers, we just use ones and zeros, and you can only have a 1 or a 0 in place at one time. If you can capture light and therefore code with solid light, then it gives you the capability, because of the speed, okay, it gives you the capability of using ones and zeros at the same time, okay, or at least relative to us it would be the same time. Now if that makes no sense to you and it's super boring to you, that's cool. Or if it's really interesting to you, look it up. There's tons of scientific articles out there about solid light, the benefits, and whether it's actually even happened. Okay, it's very difficult to demonstrate this. You know, we've seen pictures of the crystals and stuff like that, and what seems to be possible that solid light was trapped in that crystal, but I think the most amount of time anyone's ever trapped it was like 5 seconds. So, and I'm not taking anything away from individuals who designed these, okay, but in order for computing power, we're going to have to be able to trap it for a lot longer than that. Okay, but regardless, 4 states of matter. Now, part of you know, the interesting piece and things that you've probably heard in your life, you know, matter is neither created nor destroyed, but rather it is changed or recycled over time. Right? This is the exact premise that the first law of thermodynamics is based off of. Okay, energy is neither created nor destroyed. And most of you have heard these comments. Okay, and we'll go through this quite a bit in this course, because often we'll talk about, well, are renewable resources worth it? Are non-renewable resources worth it? Is global climate change real? Is, you know, are the oceans actually warming? How much of that is natural cycles and this kind of stuff? But remember, if we're talking about energy, and let's say you dig up a hunk of coal and you burn it, okay, that's not going away. The energy in there is escaping. Okay, if you burn it, okay, in a fireplace, some of it's escaping into the walls. Okay, some of it's escaping into the open spaces of your house. Okay, that's ideal if you're heating your house with it. Okay, but a lot of that energy is also escaping out of the chimney. Okay, escaping out of the chimney stack, and etc., etc., etc. Okay, because energy is not created nor destroyed. It just changes form. Okay? It can be trapped for, you know, a certain amount of time, okay? But nonetheless, energy will change form. So if it's going into the atmosphere, it shouldn't be a surprise to some individuals, okay, that it could get trapped in the atmosphere, okay, because of that property of thermodynamics. It's not created nor destroyed, it just changes form, changes shape, changes form, recycled over and over again. Now, you know, either you're looking at energy with the first law of thermodynamics, or you're looking at matter. It really makes no difference. They're both on the same kind of premise. Okay, if we're just talking about matter, the term is conservation of matter. When you know, talk about not being destroyed, but simply transforms, we could call that the conservation of matter. Okay, but we could say the same thing about energy, and a lot of times that's what we're talking about in, you know, this class is energy, because a lot of natural resources, the whole basis behind the natural resources is obtaining energy. We use a massive amount of energy, okay, whether that be food energy, whether that be energy to drive your vehicle, whether that be energy to heat your home, whether that be energy, you know, to run lights, whether that be energy, on and on and on and on. Okay? Energy is key, okay? And we'll talk a lot about it. Now, that doesn't mean there's not other matter out there that's also important as a natural resources. Wood products, okay? Soil products, rock products, okay? Water. You know, there's a lot of other matter, other resources out there that we need to talk about, and we will. Okay. All right, so first, dive into some just basic chemistry. Okay, so matter consists of elements, okay? And of the elements that occur, okay, depending on what source you're going with, there is 118 elements. Some sources say there's 122 elements. Okay? Regardless, really, a lot of the elements over, basically over the top 60 elements, anything outside of that realm, some of them are created by us in laboratories, and they don't exist for very long. Okay, so if there's other elements that have been created in laboratory space, okay, that could add to this 118 elements, great. Maybe there is 122. It's the premise behind that, though, is if they don't last very long, at least for natural resource management, we don't really need to talk about them because they're not going to be part of our scheme to either increase energy or increase supply, etc. Okay? So the elements that we're mainly interested in are bioelements. These are elements of life. Okay? So oxygen, carbon, hydrogen, nitrogen, that makes up about 96% of all the living organisms. And then we'll talk about some other elements like phosphorus, zinc, okay, and we'll talk about some of these other magnesium, other elements that are also important for living organisms as we progress. Okay? So an element itself is composed of atoms. Okay? Atoms are the smallest known particles that have characteristics of that element. Okay? And what I mean by that is each element has an atom, and that atom consists of three main things: protons, neutrons, and electrons. Okay? So when we look at an atom, okay, or an element, okay, so we look at a periodic table, and we look at an element on the periodic table, it has protons, okay, or proton, neutron, okay, or maybe not, okay, and electrons, okay, and this gives it really the property of that element. Okay? So here you can kind of see just a diagram of that. Okay? Protons and neutrons are inside what we call the nucleus. Okay, we'll talk about other nuclei or nucleus in this course, and those are living cell nucleus. Okay? Nucleus really just means core. Okay? And so if we're talking about atoms, the core is made of protons and neutrons. Okay? If we're talking about like cells, it's often made of DNA and a nuclear envelope, and then places where ribosomes are made, which is called the nucleolus. Okay? These places, and there's association with some RNA and things like that. We'll get to this information much later in the course. Okay? And then around that nucleus are some orbitals, and orbitals are where you're most likely to find electrons. And so here in this diagram, you can see these electrons are kind of spinning around this nucleus. Okay? So there's a couple numbers that you'll often see, especially if you're looking at a periodic table. You'll see the atomic number, which is the number of protons that you would find in that element. Okay? And then there's the mass number, and that's the number of protons plus the number of neutrons. Okay? Now, you can change the mass number without changing the element. Okay? So you can add neutrons or take neutrons away, and this happens naturally in nature. Okay? And that changes the mass number. Okay? But you cannot change the number of protons without changing the element. If you add a proton, you get a new element. If you subtract a proton, you get a new element. Okay? So the protons, or the number of protons, is very specific to the element that we're talking about. Okay? Now, when you change the number of neutrons, of an element, okay, you get an isotope. Okay? Now there are different forms of every element, or almost every element that we know of. There is isotopic forms, meaning that they differ in the number of neutrons. Okay? And one that's really familiar to most people is things like carbon-14. Okay? We know that that's an isotope. Okay? Because the normal isotopic ratio for carbon is 6 protons, 6 neutrons, and 6 electrons. Okay? And that's carbon-12. Okay? But if you increase the proton by 1, you would get 6, or increase the neutron by 1, you would get 6 protons, 7 neutrons, 6 electrons, and you would get carbon-13. And then if you do 2 neutrons, okay, you get carbon-14. Okay? And that's how isotopic elements work. Okay? And we'll talk a lot more about it, because we'll talk about a little bit about radioisotope dating. So how do we date fossils and rocks and other artifacts, even human artifacts. Okay? And then we'll talk about potential medical advances with it. Okay? And the reason why this is important is because some of the material that we get for these medical advances, or we get to do these tests, sometimes this material is removed from the ground, okay, in different ways. Okay? It's elements that are being dug up, okay, and captured and then utilized by us for different tasks. Alright, so let's look at chemical bonds. Chemical bonds is nothing more than really 2 or more atoms joined together, but how are they joined together? They're joined together by sharing, or often by sharing electrons. Okay? And so sometimes it's not a matter of sharing electrons, but rather it's just a matter of opposite charges, like ionic bonds. Okay? Like sodium chloride. Sodium has a positive charge, chloride has a negative charge. Okay? And when they come together, they are neutral. Okay? So they're not really sharing electrons. That's an ionic bond. Ionic bonds are very weak, relatively speaking. Okay? And but they most often result in a fairly stable structure in a crystal form. So if you look at salt under a microscope, it's going to kind of form these little crystals, okay, and you would know that that's an ionic bond. Okay? Covalent bonds are the sharing of electrons. Okay? And so the sharing of electron can be equal between 2 atoms, or it can be not equal between 2 atoms. Okay? If it's not equal between 2 atoms, it results in a polar molecule. Okay? And so that means that one side of the molecule that's formed is going to have a positive charge, and the other side is going to have a negative charge. Okay? We'll come back to covalent bonds because they're important for processes like photosynthesis and cellular respiration. Like, how do organisms convert energy? Okay? And then another bond type, which is directly related to covalent bonds, is hydrogen bonds. Okay? And that's based on electrostatic attraction. Okay? So it's kind of like a combination between a covalent bond and an ionic bond, because water itself forms a lot of hydrogen bonds. Okay? And water is the result of a covalent bond, but the bonds it can form are hydrogen bonds often, okay? Which means there are electrostatic attraction between hydrogen and some other electronegative atom. Okay? We'll come back to this. If it doesn't make a lot of sense, we'll look at direct examples of all of these in a little bit. Okay? So that brings me to the giving up or gaining of electrons. So often we'll look at reactions where electrons are being lost, okay, and gained by something else. Okay? These are called oxidation and reduction reactions. Okay? if an atom gives up an electron, it's considered oxidized. If the atom gains an electron, it is considered reduced. Now I know for some of you, you always think of reduction means you're losing things, okay? But in this situation, reduction means you're gaining electrons. Okay? These are called redox reactions, or abbreviated as redox reactions. So every time an atom gives up an electron, the opposite has to be true. Another atom has to gain an electron. Okay? So oxidation and reduction reactions have to happen together. Okay? And when we look at these processes of oxidizing or losing electrons and gaining electrons being reduced, it's very, very important for things like cellular respiration or how organisms gain energy from food, even how organisms like plants gain energy from photosynthesis or the using of photons to drive work. Okay? Now, to form a bond, to get two atoms to come together and share electrons, it takes energy. To break that bond, it might take a little bit of energy to break that bond. It depends on the type of the bond. But once the bond is broken, it releases energy. Okay, so photosynthesis is going to use photons to build carbohydrates, sugars. Okay? We're going to eat plants that photosynthesize. Okay? And then we're going to break down those carbohydrates that they made to release energy. Okay? And that's a kind of a beautiful process of photosynthesis and cellular respiration. It's a giant cycle that we'll talk about later. Okay? Now, sometimes, like I said before, to break the bond or to start the reaction, you need activation energy. You need a little bit of energy. And you can think of this as, getting enough energy to strike a match. Okay, so running the match across a pad or whatever is enough energy to cause friction to get the match to light. Okay, and now you have some activation energy in the match to light a fire. Okay, so it took a little friction, that's your energy, to light the match, and now it's going to take the match, which is also activation energy, to light wood or paper or whatever you're lighting on fire. Okay? So you can think of it the same way. You take a little bit of food in, it takes some energy to masticate it, okay, and crunch it down. It takes some saliva and enzymes and things like that to start digesting it. Also takes a little energy to start the process of churning in your stomach and things like that. Okay? But then once it's been broken down, the absorption can happen. Okay? You're going to absorb the energy. You're going to break it down again, and through processes like pyruvate processing, the Krebs cycle, glycolysis, okay, all these other processes will help you break down those sugars, or whether it's proteins or fats or whatever we're talking about, breaks it down and allows you to utilize that energy. Okay? Now, ions are just atoms that have a charge to them. Okay? They can either have a positive charge or a negative charge, and that really has to do with, do they have more electrons? If they have more electrons, they're going to have a negative charge. Okay? If they have less electrons than protons, they're going to have a positive charge. Okay? And remember, that's pretty self-explanatory, because electrons are negatively charged, protons are positively charged, okay? And so that's where you get this difference in ions. If the atom has a negative charge, it's called an anion. Okay? If the atom has a positive charge, it's called a cation. Okay? Acids are any real substance that can release hydrogen ions into solution. Okay? Most of the time into water. Okay? But you can also have other solutions at which hydrogen ions can be released into. Okay? And so really we just consider acid any atom or molecule that can release hydrogen ions. Okay. Bases are substances that bond with hydrogen ions. So they readily bring in hydrogen ions and absorb the hydrogen ions, bond it up. Okay. And that brings us to the pH scale. The pH scale is nothing more than examining how many free hydrogen ions you have in solution. Okay? So if you have a lot of hydrogen ions in solution, it's considered acidic, and it's between 0 and 7. Okay? If you have the neutral amount, so you have the same amount of hydrogen ions as you do hydroxide ions, okay, which is just the result of breaking water. So if you break water up, you get hydrogen plus and oxygen bound to hydrogen negative. Okay? The oxygen bound to hydrogen negative, that's a hydroxide ion, and the hydrogen positive is a hydrogen ion. Okay? And so if the number of hydroxide ions and hydrogen ions are the same, or we have pure water, okay, it's neutral, 7. Okay? If there's more hydrogen ions than hydroxide ions, it's acidic. If there's more hydroxide ions than hydrogen ions, it's basic, 8 to 14. Okay? And so here you can see just a table of many things that we would consider acidic and many things that we consider basic. Okay? Again, it's just the concentration of hydrogen ions compared to pure water or distilled water. So again, pure water is going to be the same number of hydrogen ions as hydroxide ions, or neutral. Okay? You increase hydrogen ions, you decrease the number on the pH scale, and you increase acidity. Okay? So if we're talking about very acidic things like hydrochloric acid, battery acid, even your stomach acid, lemon juice, okay, it's down here on the pH, okay, because they have a lot of hydrogen ions. You go the opposite way, you have very few hydrogen ions, okay, and you have a lot of hydroxide ions, okay, you're going this way. So bleaches and drain cleaner, oven cleaner, okay, is on this side of the scale. Okay, hope that makes sense. We'll approach pH scale again. I just want to give you kind of the basic chemistry behind some of these things. So when we start talking about acid rain, and we start talking about, you know, when lakes and streams and even oceans go anoxic, and maybe it's because of a pH imbalance, or maybe it's because of an influx of organisms due to phosphates coming into the water and these kind of things, you'll know that what we're talking about when we're talking about water chemistry and things like that. Okay? So stay tuned, and we'll pick up talking about more in-depth chemistry or molecular chemistry next time.